We live in a world transformed by modern science. We look to science to cure diseases, fill the future with mind-boggling inventions, and keep us from destroying the planet. What are these hopes based on? Does science have some remarkable power? Is there a scientific method that we can count on to produce miracles? Sir Francis Bacon was a spokesperson for the scientific revolution. This prominent philosopher of the Renaissance rose to the rank of Lord Chancellor of England before he was convicted of accepting bribes. After a short time in jail, he retired to write and to conduct scientific experiments. In one book, Bacon imagined an island he called the New Atlantis, where people had mastered nature through science and even devised machines like helicopters and submarines. Closer to home, Bacon criticized the schools of his day for concentrating on scholarly texts, and he urged people to open their eyes to nature.
Let us establish a chaste and lawful marriage between mind and nature. Knowledge and human power come to the same thing, for nature cannot be commanded except by obeying her. Enough if, on our approaching her with due respect, she condescends to show herself.
He believed that the constant attention to book learning was wrong, and he formulated, I think without fully knowing how his words would be used, this idea that what we must go out and observe the world. The book must be the book of nature, which must teach us everything which is to be learned about our material life.
Although Bacon put observation of nature first, he also placed a high value on reflection.
The men of experiment are like the ant. They only collect and use. The reasoners resemble spiders who make cobwebs out of their own substance. But the bee takes the middle course. It gathers material from the flowers of the garden and the field, but transforms and digests it by a power of its own.
Bacon urged scientists to use a method which he called induction. Make a number of observations, look for general patterns, test those patterns, and finally, grasp the underlying laws of nature. In many ways, induction is a thought process we use every day.
Most of the kinds of conclusions that we come to, most of the practices that are embodied in how we behave are inductive practices, are practices that come from making particular observations and some small generalization and then acting on that or trying it out.
I think there are, first of all, there's a bunch of questions about what sorts of inferences do scientists make, to which I want to say, well, many of the same kinds of inferences that historians make, legal scholars make, you or I make, the same kinds of inferences I make when I ask myself, well, how come when I cooked that dish tonight, it was so much better than when I cooked it last week? Was it better tomatoes, or I browned the onions more, or what was it? I think a lot of the inferential processes are quite common.
A critical step in scientific induction is conducting experiments to confirm connections between events.
What we're doing is setting a trap as best we can to trap nature and get one of her secrets. We're deriving an implication of an observable event from the assumption of another observable event, at which point we can set up our experiment and find out. So there's the trap in which we're hoping to get nature to express herself.
Bacon wrote in an opportune time. Several decades later, scientists who founded the Royal Society of London used his ideas to formulate their goals.
Bacon's experimental approaches of his own were not remarkably wonderful or remarkably successful, but he did sort of lay down these principles, and the Royal Society adopted the Baconian creed. And it was officially there in the Royal Society's history from the beginning. And so because of this start, this sort of Baconian advertisement, the Royal Society's acceptance of this idea, inductivism had enormous cachet, I think, through the 18th and 19th centuries, especially in Britain. And that was further reinforced by the apparent great successes of people like Boyle and Hooke and Newton and so forth. It looked as though this was the way to go.
From a modern perspective, though, it is highly debatable whether the scientists of the Royal Society practiced induction as uniformly as they believed. How much common ground was there really between Robert Boyle's discovery of how pressure affects the volume of gases and Isaac Newton's theory of universal gravity?
You see a difference between the kind of mathematical science that Newton is doing and that Descartes was doing before him, and the sort of nitty-gritty experimental detail that's typified by somebody like Boyle. Boyle builds a pump and collects lots and lots of observations on the spring of the air. Newton works out the mathematical problem of how two bodies would interact if there were an inverse square law of attraction between them. Now, Bacon's account seems to work more beautifully for the Boylean sciences, the experimental sciences, than it does for the theoretical ones. Although Newton himself, I'm sure, would have said, you know, on his deathbed, I have followed the true road of Francis Bacon.
Newton did, in fact, describe his theory as inferred from the phenomena based on observations of falling objects and orbiting planets. And for centuries, most scientists and philosophers agreed.
During the 18th century, after the enormous success of Newton's work, especially Newton's mechanics and theory of the universe, there was a sort of official empiricist account of how scientific knowledge was developed. We went out, we got observations, and in light of these observations, we were able to arrive by inductive inferences at generalizations. And we could gradually systematize these, and if we proceeded carefully and deliberately enough, we would arrive at a body of well-grounded knowledge.
The history of philosophies of science it's an odd interaction between what the philosophers say and how the scientists present themselves to themselves. I mean, so that the scientists in the 17th century, most of them, certainly the ones in the English-speaking world, presented themselves as if they were doing what Bacon was doing, even when they plainly, now historians will say, weren't. Newton wasn't doing that, for goodness sakes.
But if scientists don't derive their theories from observation of nature, how do they come up with them? One alternative was proposed by 18th century philosopher Immanuel Kant through pure reason.
Reason must approach nature in order to be taught by it. It must not, however, do so in the character of a pupil who listens to everything that the teacher chooses to say, but of an appointed judge who compels the witnesses to answer questions which he has himself formulated.
Now, this is a very striking image because what it makes clear is that every scientific investigation is in the nature of an interrogation, and that it is we who have framed the questions that our observations of nature have to to be used to give answers to. It isn't that nature forces on us the questions that we have to get the answers to.
Despite occasional dissenting voices such as Kant's, inductivism remained the dominant view of how science works until the 20th century. Ironically, it came under attack partly due to a new concept of gravity. In 1915, in his General Theory of Relativity, Albert Einstein proposed an entirely different approach from Newton's.
Newton would say that the sun sends off infinitely fast forces to the different planets, and these forces force the planets to go in an orbit around the sun, whereas the space itself for Newton is completely flat and has no effect on it whatsoever. Whereas for Einstein, there are no forces going back and forth between the planets and the sun. But space is not completely flat. Space has been all curved up around the sun. And the planets are just traveling a free orbit through this curved space. And for them, this is the straightest path for the planets, traveling through this curved space.
Also in the early 20th century, quantum mechanics suggested that Newton's laws of motion don't apply at the atomic and subatomic level. These events prompted philosopher Karl Popper to put forward a radically new view of how science works.
I assert that scientific knowledge is essentially conjectural or hypothetical. The great scientists such as Galileo, Kepler, Newton, Einstein, and Bohr represent to me a simple but impressive idea of science. These are men of bold ideas, but highly critical of their own ideas. They try to find whether their ideas are right by trying to find whether they are not perhaps wrong. They work with bold conjectures and severe attempts at refuting their own conjectures.
Inductivism agrees with the empiricist view that all knowledge must come from experience. Popper's position, by contrast, parallels the rationalist view that our deepest insights come from pure reason, not experience.
Popper really did kind of crystallize, just as Bacon crystallized. Popper really did crystallize another conception of science as being essentially theoretical. There had been many again immediate reasons for this. I mean, Popper was personally, but the world was collectively, bowled over by the way in which Einstein had transformed our conceptions of space and time, and perhaps even more dramatically, the way in which the quantum mechanics had transformed our conceptions of underlying causality. And Popper grew up his youth was formed in a world where Einstein and Planck and then Heisenberg and Bohr were household names. And these were people who did their work, he thought, in the head. It was the theory which transformed.
Where do new ideas and theories come from?
My view may be expressed by saying that every discovery contains an irrational element or a creative intuition. In a similar way, Einstein speaks of the search for those highly universal laws from which a picture of the world can be obtained by pure deduction. There is no logical path, he says, leading to these laws. They can only be reached by intuition based upon something like an intellectual love of the objects of experience.
In an inductivist view of science, tests are supposed to confirm theories. Popper maintained instead that the role of tests is to refute or falsify theories.
The rationality of science lies not in its habit of appealing to empirical evidence in support of its dogmas, but solely in the critical approach. Science has nothing to do with a quest for certainty or probability or reliability.
We are not interested in establishing scientific theories as secure or certain or probable. Conscious of our fallibility, we are interested only in criticizing them and testing them in the hope of finding out where we are mistaken, of learning from our mistakes, and if we are lucky, of proceeding to better theories.
So science, he says, makes fallible conjectures. The bolder, the better. We like them bold because then they have the promise of giving us a lot of information about the world. But of course, the bolder they are, the less likely they are to be true. So we aim at bold conjectures, expecting that they will be false. We try very hard, says Popper. This is where it starts to get a bit unrealistic. We all try very hard to falsify our conjectures. But if they prove not to be falsified by our experiences, then we tentatively accept them.
What are the criteria for bold guesses as opposed to talking through your hat? The bold guess which is testable is the one which has merit, and a bold guess which you cannot test against anything has no merit. So being falsifiable, being testable, becomes the touchstone of being scientific for Popper.
Inductivists sometimes envision science as one vast structure. We build it level by level, setting new knowledge on top of the old. For Popper, perceiving all theories as fallible altered, but did not destroy this vision.
Some of our generalizations turn out to be more stubborn and enduring than others. Therefore, we feel more dependable. So we're pinning what seems to be the more conjectural and less probable, less certain, on what we feel to be more certain, and the whole matter is simply afloat that way. Or a better analogy than afloat is Karl Popper's Sir Karl Popper figure that science is a great structure built on a bottomless swamp, on piles that are driven vertically, very long, sturdy piles down into the swamp, bottomless swamp, but driven far down, and many of them. And that's what keeps our science on a pretty even keel. And we keep fixing things up and restoring the balance when it's getting a little, when we find that it needs it. It's the way we get by without absolute certainty.
Philosophers have challenged Popper's view of science on various grounds. Most simply, the same question that Popper posed against inductivism can be posed against his emphasis on falsification. Does science really work that way?
How many scientists does one know who actually go out deliberately trying to falsify their hypotheses? And then, what's this sort of tentative acceptance stuff? I mean, we rely on science in all kinds of contexts when human lives are at stake. I mean, can our acceptance really be that tentative?
Among Popper's critics, one offered a broad new perspective of his own. Thomas Kuhn says of Popper,
"He is convinced that growth occurs not primarily by accretion, but by the revolutionary overthrow of an accepted theory and its replacement by a better one. Episodes like these are very rare in the development of science. I suggest that Sir Karl has characterized the entire scientific enterprise in terms that apply only to its occasional revolutionary parts."
Thomas Kuhn brought historical perspective to the question of how science works. Through detailed study of various sciences in different eras, Kuhn detected a striking pattern. Brief periods of revolution are set against a background of longer, calmer periods, which Kuhn calls normal science. In a period of normal science, a community of scientists works within what Kuhn calls a paradigm.
A paradigm refers to two different things, one of which is the particular achievement of solving a certain set of problems which then becomes a model of how to try to solve problems in that field in the future. And this paradigm, this established achievement and set of methods, becomes the model for scientific work in that field in the immediate future.
For instance, Newton's mechanics and Einstein's theories of relativity served as paradigms in physics during different eras. From antiquity until Copernicus, Aristotle's theory that the sun and other planets revolve around Earth provided the paradigm for astronomy. Every paradigm has some point in time when it starts to be accepted.
The success of a paradigm is, at the start, largely a promise of success discoverable in selected and still incomplete examples. Normal science consists in the actualization of that promise, an actualization achieved by extending knowledge of those facts that the paradigm displays as particularly revealing, by increasing the extent of the match between those facts and the paradigm's predictions, and by furthering the articulation of the paradigm itself. Few people who are not actually practitioners of a mature science realize how much mop-up work of this sort a paradigm leaves to be done, or quite how fascinating such work can prove in the execution. Mopping up operations are what engage most scientists throughout most of their careers.
Popper and most inductivists saw scientists as pioneers. Kuhn sees them, in periods of normal science, as ordinary people, puzzle solvers who work strictly within the confines of a paradigm. When they come upon a problem that doesn't fit the paradigm, they set it aside. But gradually, such problems mount, and a period of revolutionary science begins.
People bash their heads against a wall. It seems impossible to resolve a certain group of difficulties. And at that point, he says, we pass, that branch of science will pass from normal science into a state of crisis, where everybody's attention is focused on these anomalies and can't figure out what's going on. And then a new idea will appear, which is somehow in the same field of inquiry, but totally changes the ways in which phenomena are described. And moreover, enables one to solve some of precisely those outstanding problems.
As this new paradigm becomes established, normal science resumes.
As one person put it, Sylvan Bromberg, a nice remark, science is a series of exercises in imitation, that's the normal science stuff, punctuated by changes in fashion. Those are the revolutions.
Like Popper, Kuhn argues that scientists almost never follow Bacon's suggestion and simply observe nature. Rather, a paradigm influences what they observe and how they interpret it. Kuhn also agrees with Popper that induction does not properly describe how scientists arrive at theories.
Neither Sir Karl nor I is an inductivist. We do not believe that there are rules for inducing correct theories from facts, or even that theories, correct or incorrect, are induced at all. Instead, we view them as imaginative posits, invented in one piece for application to nature.
In perhaps his most controversial departure from inductivism, Kuhn challenged the idea that science progresses cumulatively, with new ideas building upon the old.
Kuhn says the relation between the new paradigm and the old paradigm isn't that this one sort of sits neatly on top of that. It's rather this is a completely different framework. It's got new concepts, new ways of seeing the world, new methods, all kinds of things. And so, in a very suggestive term, he claims the paradigms are incommensurable with one another.
Led by a new paradigm, scientists adopt new instruments and look in new places. Even more important, during revolutions, scientists see new and different things when looking with familiar instruments in different places they have looked before. It is rather as if the professional community have been suddenly transported to another planet, where familiar objects are seen in a different light and are joined by unfamiliar ones as well.
Some have seen Kuhn's ideas about paradigms as an argument against progress. Kuhn himself argued that science does make progress. New paradigms can be judged superior to old by standards such as scope and simplicity. But after Kuhn, it is much harder to picture science as one great structure of timeless knowledge.
I think against the background of it all, the deepest transition that he made was to think of rationality itself as being something which is historically conditioned. And I think that that change has in some way permeated a lot of modern culture.
Given the striking differences among even a few views, can any satisfactory answers be given to the questions, how does science work? And is there a scientific method?
One of the impulses that has come out of the responses to Kuhn, I think, has been the recognition of a great deal of diversity among the sciences. So perhaps it's the wrong question to say, well, look, how does science work? Perhaps we should ask ourselves instead, well, how does molecular genetics in the second half of the 20th century work?
I think we do rob ourselves, we do impoverish our understanding if we insist on only one kind of explanation, only one kind of method being truly scientific, and we enrich our ability for making the world intelligible to ourselves if we're prepared to hang a bit looser and to accept the legitimacy of all kinds of explanations.
And of course, it's not the case that science is all theory or science is all experiment. Science is an intimate interaction between what we do with our hands, what we do in our heads, and what we do by talking to each other.
And it may be at the end of the day that we have a picture of the sciences which doesn't see them in the same sort of total and monolithic way, but as a bunch of enterprises with some common features among them, that all of which, or perhaps various of them to different degrees and in different respects, are good at giving us insight into the way the world works, but that don't have sort of some shared feature that we can hail as the scientific method.
The Examined Life is a 26-part series for college credit. To purchase a video cassette or transcript of this program, call 626-796-7300 or visit us online. Please order by program number.